For this lesson, we're going to begin calculating z-scores. And bear with me throughout this lesson because z-scores become very important later on. But we'll start with a bit of an intro to them and what they mean, and we'll look at our z-scores as well as review some of the material from our mean and standard deviation lesson. So to start, let's talk about what a z-score is. Z-scores tell us whether a particular score or a datum or a specific data point is either equal to the mean, below the mean, or above the mean within a set of data. It can also tell us how far a particular data score is away from the mean, and we want to determine if a particular data score is far away from the mean or close to the mean because this will help us determine how accurate our mean is and how spread out our data is. So sometimes if I'm looking at a particular data point, it really makes a difference if it's close to the mean or is this a total outlier and it's super far away from the mean. Now when we get a z-score, and I'll show you how to do it in a second, but once we get that number, the value can tell us a few things. So if the score is equal to 0, then it's directly on the mean. If the score is equal to +1, then it is one standard deviation above the mean. Now, when we measure distance from our mean, we always measure it in standard deviations. So how many of our standard deviations is it from the mean? If a z-score is equal to +2, it's 2 standard deviations above the mean. And then we can also have our data point be below the mean. So if my z-score is -1, it's 1 standard deviation below the mean. If it's equal to -2, it's 2 standard deviations below the mean. And as we continue with future lessons, you'll begin to see why this is so important for us to know. So here's our formulas. Just like our mean and our standard deviation formulas, we have two different versions. We have one for a population and one for a sample. And you'll notice that the notation for the populations and samples from our previous lessons continues here. So if we're dealing with a population, and a population occurs when we're taking all of the possible people that we're surveying. If I'm looking at continuous data, which we'll do later in the unit, that's when we're looking at populations. But if I do have a population, my formula for my z-score is x, which is my data point or my datum that we're looking at, minus mu, which is the mean of a population, divided by sigma, which is the standard deviation of our population. Then if I have a sample, which for our purposes at the moment, we will really be looking at samples. Our formula is as follows. We have our z-scores equal to x, which is our data point, minus x bar, which is the mean of our sample, divided by s, which is our standard deviation of our sample. So again, just like before, super important to note if we are working with a sample or a population before we really get started. So let's go through a couple of examples. Now these examples will do a little bit of work with z-scores, and then we'll also take some time to review the material from our mean and standard deviation lesson. And then moving forward, we'll work with z-scores more and talk about what they mean and why they're useful. So to start, we have a chart which has the height of 6 different students. Now, because we only have 6 students, this is a sample, right? There's definitely more students out there who could have been surveyed. So this is very much a sample. So we're going to start by calculating the mean, which is denoted by x bar because it's a sample, as well as our standard deviation s. Again, it's s because it's a sample. So we'll start by calculating our mean. So for our mean, we denote this by x bar, and we sum up all of our data values, and we divide it by how many numbers we added up. So if I add up 165, 159, 162, 185, 181, and 156, I will get 1008. And we'll divide that by how many data points we added up. 1, 2, 3, 4, 5, 6. Divide by 6, and we get a mean height of 168. Now next, we're going to calculate our standard deviation. Now we already have the chart set up to help us with our standard deviation. So just as a reminder, our standard deviation formula for a sample is we take our sum of all of our data points minus our mean squared, divided by n minus 1. Remember that it's n minus 1 because it's a sample, and we take the square root of that thing. Now, because this can get a little bit messy, we have the chart all set up for us. You don't have to use the chart, but it definitely can help you to stay organized. So we'll start by doing this middle bit here where we subtract the mean from each of our data points. So that's what I'm going to do in the first blank column. So just as a reminder, my mean is 168. So I'm just going to subtract 168 from each of my data points. So we'll have -3, -9, -6, 17, 13, -12. The next piece of the equation that we'll focus on is we'll use this square here. So all of those numbers that we just found, we're going to square them. So 3 squared is 9, 9 squared is 81, -6 squared is 36, 17 squared is 289, 13 squared is 169, and -12 squared is 144. Now, we want to work with this part. So that means we sum up all of those values that we just found. So our sum here, if I add that last column there, 9 plus 81 plus 36 plus 289 plus 169 plus 144, I will get 728. So that value represents our numerator over here. So we can just put that into our equation. So we'll have the square root of 728 divided by n minus 1, where n is our number of data points, so 6 minus 1. And then you can just put that whole thing into your calculator. So 728 divided by 5, and then we square root that, and we'll get 12.07 as our standard deviation. So before we start finding our z-scores, these are two very important pieces that we need. My z-score formula requires both my mean and my standard deviation, so I need to make sure that I find those two things before I start finding my z-scores. So for part B, we're going to calculate the z-scores for Kai and Joshua. So that's the next thing that we're going to do. Now, just to make things a little bit easier for us, I'm just going to write some of the important information down here. So Kai's height was 165. Joshua's height is 185. Just as a reminder, the mean for our sample is 168, and our standard deviation is 12.07. Now we want to calculate the z-scores for these two students. And the goal here is to understand, are these data points above the mean, below the mean, and if so, how far off are they? So are they maybe an outlier, or are they very close to our mean in the middle of our data? So let's start by finding the z-score for Kai. So our z-score is equal to our data point minus our mean divided by our standard deviation. So Kai's height is 165 minus our mean, which is 168, divided by 12.07. And you can just quickly put that into your calculator, super fast, and that will give us -0.25. So what this number means is that this data point is below the mean, and it's below the mean by a quarter of a standard deviation. Now, because our standard deviation is 12-ish, 12.07, a quarter of that would be about 3. So if I look here, 165 is 3 below 168. So that does make sense when I think about it. So sometimes with nice small data sets like this, it really helps us to see what's going on with the data and if this makes logical sense. Of course, when people are working with giant data sets, this isn't always possible. So that's why we use things like the z-scores just to help give us a better sense of what's going on. So let's do the same thing for Joshua. So for Joshua, our z-score, again, we take our data point, subtract the mean, and divide that by the standard deviation. So Joshua's height was 185 minus our mean, which is 168, and we divide this by our standard deviation, which is 12.07. Again, we can just put this into our calculator nice and quickly, and that will give us 1.41. So this value is positive. That means that Joshua's height is above the mean, which we can clearly see that makes sense. And it's above the mean by 1.41 standard deviations. Okay, so that's our intro really to our standard deviations. Sorry, our z-scores. And again, like I said, we'll start using them more and you'll see why they're important and why they really matter. But we'll do one more quick example just to talk a little bit more about our mean and our standard deviation and just to practice calculating those things one more time before we really dive into more z-score work and how they're used in our next lesson. So for this example, Frank and Mona are laying patio stones and they record how many stones they put in place in 1 hour. So that's what this chart represents. And we want to start by determining which worker gets more done during the day. So to do this, we are going to use our mean. So we want to figure out per hour who is putting the most patio stones down. So on average, which means the mean, who is laying the most patio stones? So that is going to mean we calculate our mean. So we'll first start with Frank. And for our mean, we're going to add up all of our data points and divide by how many data points we've added up. So I'm just going to add up the first row, 34 plus 41 plus 40 plus 38 plus 38 plus 45, and that gives us 236. And we'll divide that by 6, and that will give us 39.33. So that means the average amount of patio stones Frank is laying per hour is 39.33. Now, because we want to compare Frank and Mona, let's also find the same information for Mona. So our mean, we add up all of our data points and divide by how many data points we added up. So we're going to add 51 plus 28 plus 36 plus 44 plus 41 plus 46. That will give us 246 over our number of data points, which is 6, which is 41. So if we look here, Mona's average is 41, while Frank's is 39.33. So that means that Mona gets more work done. So on average, Mona is working faster than Frank. Now the next question we want to consider, and this is the new part that we were working on last lesson, is which worker is more consistent? So I've just taken that chart from above and put it here just so you can see it while we're working through this. But we want to figure out which worker is more consistent. So how we do that is we use our standard deviation just to get a sense of how spread out are their data points. Does one worker consistently get a similar amount of patio stones done an hour, or does one worker have some good hours, some bad hours, but it all evens out to be a pretty good average. So let's find our two standard deviations. Now you'll notice we don't have the charts here. I want to show you how to do it without the chart. If you are on an assessment and you need to put the chart there, absolutely put the chart if you feel like it's going to keep you organized, but it's not mandatory. You don't need it. So here's how you can write it out without that chart. So we'll first start by finding the standard deviation for Frank. So just as a reminder, our standard deviation formula, we take each data point, we minus the mean, we square that, we sum them all up, then we divide by n minus 1 because it's a sample. Now we're going to do this with a chart, so bear with me. So just as a reminder for Frank, our mean for Frank was 39.33. So what I'm going to do is I'm going to subtract 39.33 from each of the data points, and I'm just going to do that first as I put things in. So 34 minus 39.33 is negative 5.3, and then I square it. So I'm going to subtract the mean and square it. Then for my next one, 41 minus 39.33 is 1.7. 40 minus 39.33 is 0.7. Then 38 minus 39.33 is negative 1.3. And then I have the same one again. And 45 minus 39.33 is 5.7. There we go. I divide all of this by n minus 1, so 6 minus 1, and I square root it. Now you can see that this is probably the maximum number of data points I'd want to add up like this without the chart, because it does get a little messy. Now I'm just going to put all this in my calculator in one go. You can absolutely break it down a little bit more if you want to, but I'm just going to put it all in one go. So that will give me 3.7. That's my standard deviation for Frank. Now we'll do the same thing for Mona so that we can compare and determine who is more consistent. So for Mona, we're going to do the same thing. We're going to start by taking each of the data points and subtracting the mean. So our mean here is 41, and it's a little bit nicer because it's a whole number and we don't need to worry about decimals or anything like that. So I'm just going to start by subtracting my mean from each of my data points and then setting it up the same way I did for Frank in the green example. So 51 minus 41 is 10. 28 minus 41 is negative 13. Then we have 36 minus 41, which is negative 5. Then we have 44 minus 41, which is 3. Then we have 41 minus 41, which is 0. And we have 46 minus 41, which is 5. Then we divide this whole thing by n minus 1, and we square root it. Oops, sorry, I should have just put a 6 here instead of the n. We know what n is, so let's just put in 6. Now I'm going to put this whole thing into my calculator. I'm just going to do it in one go, but of course you can break it down a little bit if you would like to. And that will give us 8.1. So if I look here, although Mona lays more patio stones on average, Frank is more consistent because his standard deviation is lower, right? That means most of Frank's data points are closer to the mean, whereas Mona's are very, very spread out. So what we can say is therefore, Frank's work is more consistent.